down. U is equal to this, but we were trying to solve for what? Y. So x plus or minus square root x squared plus 1. Now let's switch back. U was e to the y.
Yeah.
So e to the y is x plus or minus square root x squared plus 1. Now the natural log. Now it can come in because you have a single e. So I take natural log on both sides of this equation. Natural log of e to the y is just y. And over here, natural log of x plus or minus square root x squared plus 1. Close it. And we almost have what we were trying to show. Close enough, right? Why is it not minus? So, because what? Natural log can never be negative. Sorry, you can never plug a negative into a natural log, right? But what makes you think that this is going to be negative? Like x minus a number doesn't have to be negative, right? What's 4 minus 3? It's 1, right? That would work. 10 minus 7. So the only way we could throw out this negative is if we could guarantee that this piece over here is always going to be bigger than x. And you can guarantee it. Because x, square root of x squared plus 1, do you agree, is always bigger than square root of x squared?
Yeah.
And that's x, basically. So if this guy is always bigger than this guy, then that means when you take this and you subtract it from x, that will give you a negative number. And that's no good. So we just throw that out. And then stop. All right, so the moral of the story again was that, you know, you've got the toolbox, you've got the tools. Everyone here knew the quadratic formula, right? Knew how to apply it. You've done it a million times. But you've never done it like that. And it goes to show you that, you know, there are certain tools that we have. You just never use them in certain ways. It's like a hammer, right? I mean, you can use a hammer for a lot of different things, not just driving a nail into a piece of wood. So, you know, this was kind of like driving a screw into a piece of wood. You could do it with a hammer. That's what we did. We forced this thing to work. All right. Has anyone ever seen that before? Like a quadratic formula used to solve where you have two variables in an equation like that? No?
That's why
Okay.
I thought it was like,
Yeah, your instinct was good. I wanted to encourage you. The reason I didn't is because of that right there. I don't have enough time. But that was good. And you were thinking completing the square. And you said completing the square, but you were looking at the other side. But if you would have completed the square on the other side, it would have worked too. So different ways to skin the cat. I've said that you know, a lot of math at this level is about confidence. You know, just feeling like you can do it. When you walk into a test, not coming in defeated. You know, having that belief in yourself. You know, because I can guarantee you, if you're defeated when you walk in, then you know you're probably not going to do well. At least if you walk in confident, you know, you've got that kind of swagger to you. Not arrogance. There's a difference, right? So you got to just be willing to take the risk. Try the quadratic formula. Go for it. See what happens. All right. Can we find the derivative of this? I haven't even, have I given you a formula for the derivative of the inverse? Have I given, it's on the sheet, right? But have I given you a formula for it? I haven't, right? So all we did was I introduced you to these three. I said the other three in the book, but we never use them. And I have not given you the derivatives of them. And I now want us to show that the derivative of the cosine hyperbolic inverse function is this.
are we doing like the derivatives of cosine is 1 over sine or 1 over sine hyperbolic?
The derivative,
I mean sine.
but this is the inverse, right? All we need to do is go up to this right here. Oops. Right there. There's our cosine hyperbolic inverse function, right? There it is. That's the definition of it. How do you think they came about this formula? Same way I just did that other one, right? But they did it for cosine instead. So if we're asked to show that the derivative of that is, I scrolled down or scrolled back up, but all I have to do is take derivative of this, right? So I'm just going to take derivative. I don't want people to be confused. I'm not asking us right now to prove that this is true. All right? We're going to just take this on faith that this is true. What we're asking now is to show that the derivative of this is this right here. You see that right there? We just want to show that the derivative of that inverse hyperbolic cosine function is this. So I go back up to the inverse hyperbolic cosine function. There it is. And I'm just going to take its derivative. So you're going to take the derivative of a natural log, right? So the derivative of cosine hyperbolic inverse is the derivative of natural log of a bunch of junk, which is 1 over, pardon me? I thought you asked a question. No? No? Okay, I thought I heard that. Okay, so derivative of natural log of a bunch of junk is just 1 over all that junk, right? Times the derivative of the inside of the natural log, the argument of the function. So times, I should put parentheses maybe, yeah? Because I've got two terms in here. Derivative of x is 1. That's nice. Plus, oh man, now the derivative of the root of something. 1 over 2 times the root of that something. 1 over 2 times the root of that something. Still not done. Chain rule with this. Derivative of the inside, 2x, and that gets tacked on right there. The 2's will cancel, and I can try and clean up. Right? Okay. 2's cancel. So here's where I am. Now we kind of already know what it's supposed to be because we were told to show that it's equal to something, and that wasn't it, right? It was a lot better looking than that. Get a common denominator where?
Right there.
Right here on this? Any reason why?
So that then you can multiply across and then it will cancel.
Okay, very good. So this again is going to that whole thing of instinct. And I'm not even sure if this is as much instinct as that you've probably done so many common denominators that you see it, right? But that's what I mean by instinct. You've done so much of this. So what's being seen here is that if we get a common denominator here, I'm going to have to put this root right here on the bottom and the top, right? And then when I put those two together on top, I'll have that root plus x. Ah, the root plus x is here too, and they'll cancel. If you don't see that, it's going to be hard to know what to do next. That's what we'll do. So here's my common denominator. I put root x squared minus 1, or root. I'm doing way too much detail here, but hey, it's okay. All right, there's just rewriting the 1. Now I have the same denominator. Now I push them together. And when I push them together, do you all see that canceling happening? It's about to happen. So this now becomes this plus this over the common denominator, right, which is just this root. And now this entire thing and this entire thing are exactly the same, and there's multiplication, so you can cancel them out. And you're left with 1 over root x squared minus 1. There you go. That's what we were trying to show, right? All right. Now, the other derivatives are on the formula sheet, but we've just proven one of them. Okay, we've done all that. We've done that. All right, I have 10 minutes. I think I have enough time to at least introduce you to this idea. This is the last topic. I said I would get back to it. I'm just not going to be able to get as far as I wanted to with it, so we'll kind of pick up with this next time. it turns out that cosine hyperbolic function that we said looked like a parabola is actually not a parabola, right? We kind of established that. But it turns out that if you take a wire or a rope or something like that, and I don't have a good rope. I had one in my office. I forgot to bring it. All right. Do you mind holding this one? You can stand way over here so you're not on camera. Do you mind? So in the real world, under the influence of gravity, wow, it's too rigid, sorry. If you were to hang a wire or a rope under the influence of gravity, it would sag and it would create this thing that would look parabolic, right? But it's not a parabola. If I go out like this, it's still going to hang like that. It's still going to be a shape, but it's not a parabola. It is guaranteed a hyperbolic cosine function. All hanging wires are hyperbolic cosine functions. Even if we pull it really, really tight, that is some hyperbolic cosine function. Good, you can let go. All right. That means that it's a useful function, right? Because let's say you are working for a company that has to put up poles and you have to suspend wire between them. Let's say power, right? You're going to run power for a city and you've got these huge cables, right? Like, I don't know if it's steel. What are they, copper? What do they use? For the big high-powered lines, what do they use?
Lines?
Not telephone,
Like electricity?
like electricity.
It should be called.
I don't know if it's copper. Huh. I should know this. Okay, all right, well, I'll look it up. So let's see if you hang the wire, right, they put some tension on it, right? Put some tension. There's a lot of force on those wires. 'Cause they're pretty thick cables up there, and there's a lot of it. There's a lot of mass there. So they're hanging, right? Well, the way that they actually connect them to the poles, they don't just like bolt them into the poles, right? They can't touch the poles because they touch poles, your electricity is going to ground, and what's the point, right? So they have to insulate those so that they don't touch the pole. So what do they use? Have y'all ever seen them? Next time you're driving down the road, instead of texting, just look up for a second at a pole, and you'll see this like grayish. They're usually gray. They look like this. They're kind of like, I don't know. I don't know if
Little
you,
pencil holder, yeah.
no. Just kind of look up there. That's what I see up there. It looks, it's like this gray thing. It's either ceramic or something. It's some non-conductive material that electricity can't pass through. And every wire that comes to a pole usually it comes into this, I should have drawn it at an angle. Imagine it's like there's that thing right there. And it comes in and it stops there. This end is connected to the pole. This end's connected to the wire. Then on the other side they have another one. They have the wire going this way. And they just do a jumper wire straight across like that. And so the electricity comes here, can't go through the ceramic insulator, has to go across and then continues, right? So if we're doing this, physics, right, we need to make sure this is strong enough to hold the force of this wire. And what's going to be important to us is knowing the angle that wire is coming into that pole at, right? Like if the wire's sagging quite a bit, right, like this, then the angle right here is going to be smaller than if we pull it very, very taut, right? Then it's going to have a larger angle. Do y'all see that? Well, how could we go about figuring out what that angle is? We could, let me get this one out of here. If I wanted to know that angle that goes between the wire and here, anybody have some idea of what I could use? A tangent line, very good. Since this is a curve, right, and I've told you this is a cosine hyperbolic curve, if I could find the tangent at that point, that's where I connected it. If I could find the tangent line, right, then that line would form an angle, wouldn't it? So I need to be able to take the derivative of this hyperbolic cosine function, which is simple, it's sine hyperbolic, right? And then I could, from there, get the slope of the line, and then I could use rise over run. I could find angles, and I would be able to figure out what that angle is. Kind of get the idea? Yes? No? I mean, you get the general concept. I don't have enough time to work through the problem. So these have a special name, catenaries. I don't know if I'm pronouncing that right. I think it is.
Yeah, it's
Catenary.
It's aluminum, by the way.
It is aluminum for those big. Yeah, they don't use copper. I think it'd be too expensive. I don't think aluminum lasts as long, but I think copper. I don't know if it would hold up to the tension either.
Yeah, well, it's
It would probably rip apart.
sometimes reinforced with steel.
Yeah, I would think that they do some sort of protection over. Okay, so any time you have a hanging wire on any planet that's under the influence of any gravitational force, you're going to have this shape. All right, and all of them are going to follow this formula right here. This is the general formula for a hanging wire. So x in the problem is your variable, and then a is some constant. A is going to have an effect on the shape of this thing. Like, is it stretched really tight, or is it hanging like, really low? And then c is a constant that just moves the graph up and down. So I've got kind of an animation over here where I can adjust. Pardon?
Homework.
The homework's down here. I'm going to get to it. Yeah.
Are we going to sign into it? Yeah.
I don't remember, but if it is, I worked through the whole problem, so you'll be able to follow it. So see how I adjust A and it changes the shape there? And if I adjust C, all that does is moves it up and down. All right? All I wanted to show you with this is that these hanging wires are not parabolas. If I take a parabola and I try and fit that orangish yellow one as a parabola, if I can try all day long and try and fit these two to be right on top of each other, and it would be impossible. All right? So you cannot model a hanging wire with a parabola. There's your homework. What you see in yellow was not, if you're looking at your notes in Canvas, all right? If you look at the notes in Canvas, I just assigned 26 through 41, 47, and 48. These are problems that I've added to the assignment for you to do. All right? I'll leave that up on the board. I'll make it a little bigger. I have 2 minutes. Can I ask you all a question? And plus, you have to sign in. Where'd that sign-in sheet go?
Behind your water bottle.
Yep, there we go. Okay, I started it last time here. I'll start it this. So be quick, okay? Initial, move on. I know the dates are still wrong. All right, everyone see that okay? All right, how do y'all feel so far? Y'all okay? I mean, in my college algebra class that meets the math 13, 14, we spent 45 minutes like, hey, what's your name? What's your major? We were like having fun. We wanted to have a pizza party on the first day, man. We were just having so much fun in that class. Okay, this is Cal 2. I know, I mean, it's the pace, like I said, is never going to stop. But are y'all feeling okay?
Yeah.
It's hard to gauge from my end, like if y'all are like,
I think the lecture video is really helpful.
okay, we'll see how it continues. Remember that I have other videos from other semesters that if you ever wanted to watch ahead of time, you could. All right. Everyone needs to sign in. I'm sorry, normally I will remember that beforehand, but
Professor, fun fact, the St. Louis Arch was originally built with a
Uh-huh.
hyperbolic curve,
Uh-huh.
and then it actually fell down in models that they made.
Uh-huh.
They had to use a catenary.
really, I didn't know that. Well, you would think that whatever gravity forces to be the best shape, right, this way, should be the best shape strength-wise the other way too, right? Kind of the reflection of it.
Well,
That's it. I didn't know that.
It was fine when gravity affected it,
Mm-hmm.
but if they had winds over 15 miles an hour, with
Uh-huh.
it being so tall, it would just
was-
topple over.
What did they use initially?
They
A
used
hyper-
a